In this video, we're going to talk about who won the 2025 Nobel Prize in Physics and why they were awarded, explained in complete detail. But before we dive into that, you have to first understand these things better. An electron exists as a cloud of possibilities, called a probability cloud. Now, this cloud can take different shapes depending on the energy state of the electron. Scientists describe each of these shapes using what's called a wave function, and every different shape corresponds to a different wave function. All right, let's get started. Look around you. Everything you see is made of atoms, and around every atom there are electrons. Now imagine using a special particle detector to find one of those electrons somewhere in space. When we detect it, what we see looks simple. Just a tiny glowing dot on the screen. That's what we usually think an electron looks like. But here's the strange truth. It only looks like that because we've measured it. The moment we observe the electron, it takes on that neat, particle-like form. Before detection, though, it's something completely different. It doesn't look like a dot or a ball at all. Instead, it exists as a cloud of possibilities, something that looks more like a hazy puff of smoke spread across space. This is what scientists call a probability cloud. It's a mathematical description that tells us the chances of finding the electron in different places. But many scientists believe this isn't just a math description. This cloud might be physically real, representing how the electron truly exists before observation. What's even more fascinating is that this cloud isn't empty or imaginary. It carries the electron's charge, energy, and mass, even though it has no fixed shape or boundary. And the instant we make a measurement, something extraordinary happens. All those possibilities collapse or merge into one single outcome. The scattered cloud suddenly focuses into one spot, and that's when an electron appears in reality, the tiny dot we see on the detector. Now, as we know, electrons behave like probability waves before they are observed. So let's think of an electron purely as a wave, not a tiny particle. Atoms are said to have different energy levels around them, and electrons are often described as occupying these levels. But in reality, there are no physical layers or shells floating around the atom. These energy levels are actually different ways the electron's probability wave, called the wave function, is distributed around the nucleus. Let's take the hydrogen atom as an example. In its lowest energy state, or the ground state, the electron's wave spreads out smoothly in a spherical cloud around the nucleus, like a soft, glowing mist centered on it. When the electron absorbs energy, something interesting happens. Its wave doesn't turn into a faster-moving particle. Instead, the whole cloud expands and changes shape. The new, larger cloud represents the electron in a higher energy state. Between these states, there are thin, invisible zones called nodes, where the probability of finding the electron suddenly drops to almost zero. You can think of them as empty spaces between different standing wave patterns, like the silent spots on a vibrating guitar string. If the electron gains even more energy, its wave pattern becomes more complex. The cloud might stretch out and form lobes, like a three-dimensional flower with petals in different directions. These are called pp orbitals, for example, 2px, 2py, and 2pz, each one oriented differently in space. So, when scientists talk about electrons jumping between energy levels, they're not talking about particles hopping from one orbit to another. What's really happening is that the electron's wave pattern changes shape. It reorganizes itself into a new stable form that fits the atom's potential field perfectly. Well, with all this, we understood the basics of quantum mechanics. Now, let's explore a fascinating phenomenon called quantum tunneling. Imagine the electron in a hydrogen atom. For stable state, its probability cloud is roughly spherical and centered around the nucleus. This cloud is held close by the electrostatic attraction between the negatively charged electron and the positively charged nucleus. Scientists often imagine the binding force between the nucleus and the electron as a kind of wall, called a potential barrier. Now look at this. This graph here shows the probability of finding the electron in a hydrogen atom's ground state, where its probability cloud is spherical. You can see that the probability of finding an electron gradually decreases as you move farther away from the center. But here's the interesting part. If we place this probability wave inside a potential barrier, you'll notice that at the edge of the barrier, the wave doesn't suddenly drop to zero. Instead, it slightly extends beyond the wall, meaning there is still a small chance of finding the electron outside the barrier. This is surprising because the electron doesn't have enough energy to cross the barrier according to classical physics. Yet, in a truly quantum way, the electron's wave penetrates through the barrier. This strange but real effect is what scientists call quantum tunneling. Scientists use this strange quantum effect to pull electrons out of atoms without giving them the full energy needed to escape the barrier. Here's how they do it. They apply a strong electric field on one side of the atom. Normally, the nucleus sits at the center, while the electron's probability cloud is spread evenly around it. But once the electric field is switched on, the negative electron cloud gets pulled slightly in the direction of the positive side of the field, while the heavy positively charged nucleus is pulled just a little in the opposite direction. This makes the atom slightly tilted or polarized. One side now has a denser electron cloud, and the other side has a thinner one. Because of this distortion, the potential energy landscape of the atom, what scientists call the potential barrier, becomes uneven. On the side where the electron cloud is pulled, the barrier becomes thinner and lower. The electron's wave function, which normally fades out smoothly at the edges, now stretches a bit farther in that direction, reaching into the region beyond the barrier. In this way, a part of the electron's probability cloud leaks out, even though the electron doesn't have enough energy to escape classically. Now let's talk about the 2025 Nobel Prize in Physics and see how scientists turned quantum tunneling into real-world applications, including how they use it to build quantum computers. The prize was shared by John Clark, Michael H. Deveray, and John M. Martinez, who demonstrated that quantum effects are not limited to tiny particles, but can also appear in larger, carefully engineered systems. What they actually did is use a tiny device called a Josephson junction in superconducting circuits. This junction is made by placing a very thin insulating layer between two superconductors. Normally, an insulator would block the flow of electrons, but in a superconductor, electrons form pairs called Cooper pairs. All these pairs together behave as a single coherent quantum wave, similar to the probability cloud of an electron around an atom. This quantum wave can actually tunnel through the thin insulating barrier. This is the same phenomenon we see in atomic tunneling, where an electron's probability cloud can extend beyond the binding force of the nucleus or the potential barrier. Inside the Josephson junction, the superconducting wave exists in a kind of potential well, similar to the probability cloud trapped by the nucleus in an atom. Here, the potential barrier is created by the thin insulating layer. The quantum wave in the junction can also take on different shapes when it gains energy, just like the different shapes of an electron's probability cloud around an atom. As we already know, because of quantum mechanics, the wave can only occupy specific energy levels or shapes within this potential barrier. In the lowest energy state, the wave is compact and mostly inside the barrier, with only a tiny part leaking into the walls, so the tunneling probability is very small. In higher energy states, the wave stretches further, and more of it reaches the barrier, increasing the chance of tunneling. Scientists can control which energy state or shape the quantum wave occupies by applying microwave pulses with the exact energy needed to move it from one level to another. When the wave absorbs this energy, its shape changes and it occupies a higher energy level. In this new state, the wave extends further into the barrier, making tunneling more likely. By controlling the energy states and observing the tunneling behavior, scientists can manipulate the quantum state of the superconducting circuit. This ability to control tunneling and energy levels is what allows Josephson junctions to function as quantum bits, or qubits in quantum computers. The lowest energy state can represent 0, and the next energy state can represent 1. Because the wave can exist in a superposition of states, it can be both 0 and 1 at the same time. Scientists use microwaves to move the wave between these states and read the tunneling behavior to determine which state the qubit is in. This is how tunneling in Josephson junctions is used to store, manipulate, and read quantum information, forming the foundation of modern superconducting quantum computers. The 3 scientists were awarded the Nobel Prize for building this special circuits. These circuits allow electric current to behave in strange quantum ways. They showed that even a circuit made of millions of electrons, large enough to be seen or handled, can still show quantum tunneling, a phenomenon once thought to exist only in the microscopic world. Their experiments proved that such circuits can absorb and emit energy in fixed, discrete amounts, just like real atoms do. By controlling these effects, they were able to create artificial atoms, man-made versions of nature's building blocks. These artificial atoms are now used to build quantum computers, ultra-sensitive sensors, and other advanced quantum technologies that could transform the future. This is the end of this video. Hope you enjoyed it, and don't forget to share your opinion about this discovery.